Okay, so let me start. Thank you very much for giving me this opportunity to talk about my work. This work is done with Professor Sir Michael Berry, which probably all of you know. And this is, I mean, he's famous for geometric phase. Besides many other things, he has contributed. And because I was not aware of the level of the students, level of the audience I'm going to talk to, so I have prepared the talk at a very basic level. So I hope it will not, I mean, it will be fine with you. Okay, so let me just, okay. So, okay, so the question is, the basic question is how the quantum states of a system change when its Hamiltonian is varied by changing the parameters. Basically, the Hamiltonian, as we know, is a of the usually the Hamiltonian formulation of quantum mechanics consists of two parts, kinetic energy and potential energy. And kinetic and potential energy both depends on the position and the momentum, but the potential energy also depends on the system conditions, and through system conditions, it depends on the system parameters. So even if you are not changing your position and momentum, but you are changing system conditions, then also the Hamiltonian changes, and therefore your state changes. And there, the question is, even if you are staying at the same location, same coordinate and same momentum position, how does the state change if the parameters are being changed? And this is called actually also parallel transport, where you keep the your arrow, direction of your arrow locally in the same direction, but still because of the geometry of the space on which you are walking, the direction changes. And question is whether ultimately when you have traversed all your path, have come back to the same position after completing your cyclic path, will your arrow come back to the same position, although you have not locally changed the position. So this is called the parallel transport. And this is actually leads to very important results. But before I get into that, there are actually two main questions. When you are changing the system condition, how the geometry of a given state changes. And secondly, if suppose you have started from an initial state and going to a final state, whether the initial state is different from the final state or not, even if you have completed a full circle in the parameter space. So these are two main questions, and there are two different physical properties associated with that through which these are measured. So I'm getting into that now. So one very important concept related to that is geometric phase, which now is a matter of textbook. And but let me just remind you. So a quantum Hamiltonian, depending on system of parameters R, and we are interested in, for purpose of this talk, we are interested in slow evolution of these parameters. Why slow evolution of parameters? Because if the Hamiltonian is slowly perturbed, the system remains in its instantaneous eigenstate. Okay, and that means although the parameters are changing, and the state also depends on system parameters, because you find the state by solving the Hamiltonian, and if the parameters depend on time, the state also has to depend on time, but this time dependence is very slow and you can treat the state almost not changing. Okay, so basically this is called instantaneous eigenstate, which is probably has been taught in the quantum mechanics course. But the question is, what happens if your parameters are evolving in a cyclic way and come back to their original position? So although the state depends on the parameters, and the parameters have come back to their original position through some cyclic path, whether the state has changed or not, that is a question. Now we know that our quantum mechanical state, there are two very important parts. One is the amplitude, other is a phase. And amplitude often depends on amplitude. what I call this amplitude depends on the position and the momentum, and also on the system parameters. But you have already said that you are neglecting you are saying that the state is very slowly changing with system parameters. So you assume that it is almost not changing. However, there is another part of the state, and that is a phase. And phase does change with respect to time. And of course, even if you do not have your parameters time dependent, parameters are fixed. Still, if a state is, if the eigenstate is evolving with respect to time, there is a phase which evolves with respect to time, which we all know and we have studied, and that is called the dynamical phase. And that depends on the energy level of that eigenstate, the eigenvalue of that eigenstate, and it can be obtained by the integration over time, for which you have considered the dynamics of the quantum state. But because you are now the parameters are also changing in time, it was shown by Michael Berry that the state also develops another phase, and that is called the geometric phase. And that geometric phase is given by this formula. It depends on this operator, the partial derivative with respect to time, and its overlap with the eigenstate, or the expectation value of this operator in the instantaneous eigenstate. Okay, now comes as I showed that the geometric phase depends on the time integral over time of this quantity. But you can also define another property which is called geometric curvature, which is related to geometric phase and is a lot more easier to handle and lot more important, because geometric phase is defined for a closed loop when the Hamiltonian goes around a closed loop in the parameter space. And geometric phase is usually circuit dependent because it depends on how you are traversing the parameter space. For calculation of geometric phase, you need to have a detailed analysis of closed loop, and that may lead to technical issues. So instead of calculating, it's better to focus on the quantity which you don't have to integrate, because as I said, for integration, you are integrating over the parameter space, and you need to know the details how you are going around the parameter space. But if you just consider the local quantity before integration, you don't have to do that. So therefore, it's better to consider this quantity, and by using the Stokes theorem, you can connect the geometric phase, which is expressed by this formula, to an area integral. So this was the integral over the parameter space. Okay, and this was a volume element. Now you can convert it by using the divergence, by using the Stokes theorem to the surface integral. And then that quantity which comes out is called the geometric curvature. And now it does not depend on the loop over which you traverse your path in the parameter space, and it is actually a lot more important. And it has actually much more relevance, and I'll get to that now. So, as I already said, curvature is better than phase because phase is always associated with a closed path, while curvature is a local quantity, and it gives a local description of geometric properties of the parameter space, while phase gives you the integrated information, while curvature gives you the local information. Okay, so phase does not give you information about what has happened during the circuit you have traversed, but curvature can. Both of them are gauge invariant and therefore can act as physical observable. And geometric curvature actually can give you direct information about the dynamics of parameters. No closed loop analysis required for curvature analysis, and it has also many applications. For example, there was a talk just before my talk, and that was about topological material. And again, I will use the same example. For example, it has been used in proper description of Bloch electrons, which has various effects on transport, thermodynamic properties, and topological phase transitions. Now let me, this geometric phase and geometric curvature are also connected to very important criteria, and that is topological invariant. So let me just briefly give you the basic idea. Actually, disorder phase transitions were believed to be symmetry breaking, and symmetry broken phase was believed to be ordered phase. At low temperature, symmetry restored phase at high temperature was considered disordered phase. However, when they discovered quantum Hall transition, they found that actually it is possible. Quantum Hall conductance, they found that it is actually possible to have an ordered phase without symmetry breaking. So question is, what type order caused this quantum Hall effect? This is actually topological order. In a topological ordered phase, some physical response functions are given by topological invariant. So topological invariant, as the name suggests, is the property that does not change under continuous deformation. Okay. Most of the topological invariants in physics arise as surface integrals of some geometric quantity. For example, in a Bloch theorem tells us that the single electron wave function in a crystal can be written as a phase term, as a amplitude term, and crystal momentum K is restricted to Brillouin zone. Then Brillouin zone plays the role of the surface S, and you ask how much the state changes if you go around the surface S in the circuit enclosing the surface S, and then you ask how much the wave function has changed related to this, and that is all these tools are, which is called Jacques phase, and also related to, can lead to curvature. So this is all related to, you can calculate the curvature related to the Brillouin zone by using this quantity, and this is also, so this is one application of the curvature. There are many applications, but I'm not going to talk about applications. I'll just indicate, for example, topological insulators, quantum spin Hall effect, topological metals, magnetoelectric effect. There are so many every day. Actually, if you hear any condensed matter conference nowadays, geometric phase is always mentioned, and it's actually the geometric phase in quantum systems. So, and that is actually called Berry phase. So it is that. Okay, but this is my topic. My focus is not on the topological materials, rather quantum information, and I'll now move to that. So what about quantum information? So in quantum computation, so let me just motivate you. Information in a quantum computer, as all of us know, is stored in a quantum state, and you have to operate, because quantum computer means you are doing some quantum operations on this bits of the quantum system, which are qubits or the quantum states. So you are doing some quantum operation on the quantum states. Naturally, the quantum state will change. Question is how fast the quantum state changes, how does it evolve, and how does the speed of evolution depends on the changing system parameters, because you are doing some operations. And how do you even identify whether the state has changed? That means how to distinguish between two quantum states. Secondly, quantum communication. Even if you are not doing quantum computers, you are conveying the information. That is also done in form of quantum states through quantum channels. But these channels, because if you are doing a long distance communication, which actually is the ultimate goal, then it has to, all your quantum channels have to come in contact with the noisy environment. And usually this noisy environment leads to loss of information. So your quantum state has changed, because you had used the quantum state to communicate your message. But now, because of the system, your quantum state has got in touch with noisy environment, and it has changed its state. Question is, you would like to know, if it has not changed, can you use a state which does not change very drastically when it comes into contact with the noise? Okay, so you have to find out, basically you want to know a measure, first of all, how to distinguish, how to measure the change between two quantum states. And this is a major topic for quantum error correction, quantum key distribution. And one way to do that is fidelity of the state. Basically, fidelity, if I want to tell you in a very crude way, I'll just say the overlap of the initial state and the final state in one way for pure states. But actually, there are many measures to calculate the distance between states, quantum states. Okay, so I will now get to that. So a family of states, let's call N, which depends on some system parameters R. Okay, and R can be many parameters, not xi I'm using. X is not the position variable, X is parameter. So I can take any value, not only 3 variables, I can be 1 to N. And the distance between neighboring quantum states is given by then this nr plus dr minus nr. And because these are complex, usually a quantum state is complex, so you have to consider the mod of this. And okay, now if you expand this in the Taylor series, you can write it in terms of this form, overlap between dn and dn, where what is dn? Dn is dn is the small change, because what you are saying, if you change the parameters of the state slightly from R to dr, how this state has changed with respect to its original position. Okay, so naturally you are considering the change in the parameter space. So this is how you can write in terms of the partial derivatives. So dn is like this. And now when you consider the overlap between d and dn, it can be written in a tensor form, second rank tensor form. And it is just a simple calculation to show that this Tij, because of course d and dn, when dn, it will have a cross terms also. So dxi, dxj. And now, so you have this tensor product, tensor, second rank tensor coming across, which turns out to be of this form. But this can further be written, because it's a complex number. It can be written in 2 parts. One is the symmetric part, one is the asymmetric part. Okay, so basically this, or if I want to say in a more correct way, I will say it is a second rank tensor. That means it's a matrix, but it's a non-Hermitian matrix. But a non-Hermitian matrix can always be written as a sum over one Hermitian part and one non-Hermitian, anti-Hermitian part. So now I'm writing it into 2 parts. One is the Hermitian part, other is a anti-Hermitian part, or it's better to call it symmetric part and anti-symmetric part. Now, anti-symmetric part is called quantum metric, and it tells you about the distance between 2 states, because it's like metric in any classical space. So that's why, because it tells you about the distance between 2 quantum states, that's why it is given a name quantum metric. And the other part, which is the anti-symmetric part, is called geometric curvature. And this whole thing, the sum, is another name called quantum geometric tensor. It is also called Fubini steady tensor. And okay, so it is also known by some other names. But basically the idea is now to focus on what can we say about quantum metric and quantum curvature. So as you see, both of them are arising because we want to consider the distance between 2 quantum states in the parameter space. So, of course, without getting into mathematics, let me consider, it's more important to consider, instead of, as I said, one thing, I'll go back, that Tij is a second rank tensor. It's a matrix. It's a non-Hermitian matrix, and Gij is a Hermitian matrix, and Cij is an anti-Hermitian, anti-symmetric matrix, symmetric matrix and because okay, let me just use the same word, Hermitian and anti-Hermitian part. So this Gij is also a matrix, and Cij is also a matrix. Now I'm interested in considering the trace of this matrix because it can provide a lot more information. So if you consider the trace of this matrix sum over all the diagonal elements, it can be written in this particular form. And the important thing is, by using the eigenvalue equation of the Hamiltonian, it can further be written in form of the trace of a quantum metric can be related to the level repulsion of the Hamiltonian. So let me just indicate, as you can see from this eigenvalue equation, here H is the Hamiltonian, which depends on the system parameters, and it is changing with respect to system parameters. And NR is the eigenstate, and En is the corresponding eigenvalue. And you want to consider the quantum metric trace corresponding to the state NR. Okay. Now, so as I said, that without getting into mathematical detail, it just 2 lines calculation that you can write it in this simple form. But what is M and N? M and N are the eigenstates of the Hamiltonian H, your original Hamiltonian H, and En and Em are the corresponding eigenvalues, energy levels. So basically, the calculation of quantum metric trace boils down to this complicated function, which depends on the level repulsion of the energy levels and the eigenstates of the original Hamiltonian. Okay, now the rest of the talk depends on how do you calculate that. But before that, I will also show that the curvature can also be written in the same form. Okay, and I think let me first show that. And again, without getting into mathematics, using the same equation, you can write curvature, because as I showed that the curvature can also depend, curvature is also in a matrix form. But curvature is also a second rank tensor. It's also a matrix. And but you can also consider only the 3 components x, y, y, z, because remember what was your curvature? CIJR. What was IJ? IJ were the set of parameters, parameter indices, how many parameters you are changing. So suppose if you are changing only 3 parameters, so Cij is a 3 by 3 matrix, because I can take 3 values, J can take 3 values. Similarly, Gij is 3 by 3 matrix, and Tij is also 3 by 3 matrix. So curvature and quantum metric, both of them are 3 by 3 matrix if you are changing only 3 system parameters. Okay, so as I said, in this case, in the case of the trace, I focused on the trace, but in this case, I will focus on the off-diagonal elements. And okay, because diagonal elements actually will be 0, because this is an anti-symmetric matrix, as I already said. Okay, so now you are focusing on the off-diagonal terms. And off-diagonal terms, without getting into detail, can also be, you just using the eigenvalue equation can be written in this form. Okay, now one important thing you must note, even if I'm not able to complete my talk, I want to indicate to you one important difference between metric and curvature, which both of them very important tools to analyze quantum information nowadays. What is important is that a geometric metric trace is G contains the square of the matrix elements of the perturbation in the eigenvalue basis. Delta H is the perturbation in the parameter space, and this gives you the matrix element. That means matrix elements are in the eigenfunction basis of H. Okay, but it is still a square. And this contains the square of the level repulsion between 2 eigenvalues. So one thing you notice, and this is going to be very important, that I'm not keeping time track. Actually, let me just check. Okay, 11:34. Okay, so one thing you notice, the G is going to be dominated by the, this is the metric of which state I'm interested. Look, here I am summing over M. All M is sum, so naturally, but not N. N is not summed. So this is the metric of the quantum state N of the Hamiltonian HR we are talking about. Just for simplicity, I have not put a index in here, but basically this is the metric of the quantum state N. Because M is summed over, so M is no longer, G does not depend on M. But you see, the metric trace depends very significantly by those energy levels which are very close to En, because the energy levels which are very close to En, that will make this 0 and G will shoot up, irrespective of what this, because this is always positive. So this sum can never be 0. So this will always shoot up near the level repulsion. If two near any avoided crossings of level, even if your level does not have any degeneracy, but if there is accidental degeneracy, two levels are coming very close. This is also called avoided crossing. So near an avoided crossing, this Hamiltonian, function will just shoot up. Okay, so metric becomes very large, and this has a very important meaning in context of quantum information. Now look at the curvature. Curvature also has the same form, except that the denominator is different. The numerator is different. The denominator is of the same form, contains the same power of level repulsion between two energy levels. So all those levels which come to very close to the level whose curvature you are studying, they are very important. They have a very important effect. However, this thing can also be here the numerator can be negative also. So naturally, there is a possibility of this going to 0 even if the numerator becomes terms cancel each other out. So this has in that aspect it is different. Another thing, because it is an antisymmetric term, so it also has imaginary part. So curvature is 0 if you are considering the real eigenstates. Okay, a real eigenstate has no curvature. Okay, so but that is not true for the metric, and that's why metric is curvature does not always give you all the information what the metric can give you. Okay, so now let us see one example, metric of a typical random state. And why we are looking at the typical random state, I will just come to in a few minutes. So here I'm considering a Hamiltonian, let's say, which depends on two parameters, x and y. And this Hamiltonian, just for simplicity, I'm taking very simple. There is H naught initial Hamiltonian. It is perturbed by Hx and Hy. Okay, and Hx depends on the strength by which H naught is perturbed by Hx has perturbation strength is X, and Hy perturbs H naught by a perturbation strength Y. X, Y are the parameters which can go to change. Okay. Question is now, if now you look at the nth, n is equal to, it's a 6 by 6, consider just for simplicity, a 6 by 6 Hamiltonian. And this Hamiltonian is chosen what is called a Gaussian orthogonal ensemble. That means this Hamiltonian is chosen by an ensemble of Hamiltonians where all Hamiltonians are equally probable, and okay, and they are not changing if you change the basis. So if you look at the third state of this Hamiltonian, third state just arbitrarily chosen, it's not any specific state. We are looking at the third state, and you see, and you are plotting it in the xy space. Xy, remind you, the parameter space. So what you are plotting the metric, quantum metric trace in the parameter space, because as I showed you that G depends on this has summed over M. So G is the property of the nth eigenstate, but through HR, it also depends on R, which are the parameters. So G depends on X and Y, which are the parameters in your present case. So here, so you are plotting you are asking how G changes with respect to X and Y if you choose the third eigenstate. So here the G for the third eigenstate, and you see it just shoots up. And if you look at the eigenvalue spectrum of the Hamiltonian H, you can easily connect that these shoots up are occurring where there are accidental degeneracies in the eigenvalue spectrum of the Hamiltonian H. So basically, as you can see, there are 5, 1, 2, 3, 4, 5 shoot ups, and 3 of them because the third state can be very close to the state 2 and also can have two accidental degeneracies with the state 4. So this state, as we can see from the data, which I'm not showing you here, the state number 3 has 2 accidental degeneracies with the state 4 and 3 accidental degeneracies with the state 4, and there is a shoot up. Okay, so now similarly you can do for curvature. Curvature, here there is another case for curvature. Again the same Hamiltonian, but now I'm looking at the state 10. And it is a 20 by 20 Hamiltonian. It's not for any reason. It's just because these two works were done at different time, not at the same time. So that's why here we considered 20 by 20 Hamiltonian and looked at the 10th state. And as I said, in this case, you have to consider a complex Hermitian ensemble of because the state has to be complex. Otherwise, curvature is 0. Again, you see the shoot up, and again, you can connect these shoot ups with accidental degeneracies. Okay. So question is, first of all, why I'm interested in random states? Because I showed you the picture of curvature and metric trace both for random states. Why are we interested? So let me just tell you, nowadays there is a lot of talk about many body Hamiltonians, and almost every physics, although for last 100 years or 200 years, we kept talking about the linear physics. That means in every complicated Hamiltonian, we expanded it in Taylor series near its potential minimum and approximated it by some kind of harmonic oscillator potentials or some kind of linearization and solved those Hamiltonians. But that physics is now old, and you can no longer go ahead with that physics, and you have to consider now the realistic Hamiltonians where there are a lot of interactions are going on, and almost every system has many body interactions. There is no system in universe which does not have which is just single body in reality. Okay, so therefore you cannot. And the moment you are talking about many body Hamiltonian, even 2 body, even 3 body Hamiltonian, the question is, the basic tools are we have to solve problems is matrix mechanics. Okay, so question is, can you write down the matrix representation of your quantum operator? Okay, so even if you know that there are 3 electrons interacting by the Coulomb interaction, you can write down the Coulomb interaction very exactly. So you can write down the Hamiltonian in the operator form very exactly, no doubt, nothing. But the question is, can you now calculate the matrix elements of this Hamiltonian in the position basis? For example, if you are interested in studying the problem in the position basis, or in the momentum basis, or in the energy basis, the answer is no, because you have to do some approximations when you do the integration, and you cannot solve all those integrations all the time in the known functional form, in the mathematically known functions, and therefore you have to do some approximations. So what I'm trying to motivate is determination of some or all matrix elements you can only do within an error, within an uncertainty. So matrix elements are best described within an error. This is another way to say matrix elements are best described by a probability distribution. So each matrix element you can determine only within an error, and therefore Hamiltonian is best described. Hamiltonian matrix is a matrix where each element is known only within an error or by a probability distribution. So that means you don't know exactly which matrix you should use to solve your eigenvalues, eigenfunctions, or physical properties. You only know, okay, this matrix can also be possible, that matrix can also be possible, which satisfies this probability distribution. So this is another way to say that you know your Hamiltonian belongs to an ensemble of Hamiltonians, and each member of that ensemble is equally good representative of your Hamiltonian. So basically, instead of solving a single Hamiltonian matrix, you have to consider the ensemble of Hamiltonians. Okay, but depending on what kind of complex systems you are dealing with, there can be all kind of probability distributions, and therefore Hamiltonian is a random matrix which can belong to different kind of ensembles. Now, if you know the Hamiltonian is not well defined and it is a random matrix, so how can you determine its eigenvalues and eigenfunctions? If matrix elements are distributed, then eigenvalues and eigenfunctions will also be distributed. And you just now saw that in the curvature, you can write down the curvature or the metric trace in terms of the eigenvalues and eigenfunctions of the Hamiltonian in which you are interested. But now you have to deal with the eigenvalues and eigenfunctions which are distributed. So naturally, your curvature will also be distributed. If eigenvalues and eigenfunctions are distributed, any property which depends on them will be distributed. And therefore, the curvature and trace will also be distributed. And that comes to the topic of the talk, statistics of the curvature and statistics of the metric trace. Okay, now of a random state, because almost all states which you are dealing with are states of the Hamiltonians which cannot be well defined, and therefore they are all random states, not because nature has made them random. It's because of our own ability to calculate them exactly. Okay. So if tomorrow some aliens come and tell you that you can calculate them exactly, that will be a different thing, because nature is not uncertain. Nature has given you the Hamiltonian exactly, that it is three body, three electrons interacting. It's your own limitation that you are not able to solve it. Okay, that's why you have to make use of these kind of random matrix to system dependent random matrix ensembles and all that. Okay, so let me quickly motivate you. Let me see how much time do I have. 11:47. Okay, I think it's important because for those who are like mathematically minded, let me just indicate. So how you calculate the distribution of a property, let's say F, because now I'm talking about two properties. As I showed you, you can consider a property F written in this form, V, where V is arbitrary, and this is the level repulsion, squared level repulsion. Now, if V takes this form, it gives you the information about the metric trace. If V takes this form, then it gives you the information of curvature. So I'm writing it in the combined form. So I'm interested in calculating the statistics of F for a given state N. How do you calculate the statistics of F? You ask, and why are you considering, where are you considering the statistics? You are saying, if you had a single matrix, single Hamiltonian matrix, then there would have been a single state N and you don't have to worry about the statistics. But you are saying you no longer have a single Hamiltonian, you have an ensemble of Hamiltonian. Each Hamiltonian in this ensemble has its own nth eigenstate. And you are asking, okay, let me go through this ensemble, check the nth eigenstate of each member and see what is its curvature. And I'm asking how this curvature of the nth eigenstate is distributed over the ensemble. Okay, so you are not changing the eigenstate. You are nth eigenstate you are looking. Just fixed eigenstate, but now you are going through all the members of the ensemble and checking it. Okay, so this is the formula and this is the ensemble average. So you are asking, what is the probability that the property F of the nth eigenstate takes value F? This can, because it's a Dirac delta function, it can also be written in this form. Okay, where f is fixed and fn depends on this fn I have defined here. So naturally, because if fn depends on the eigenvalues and eigenfunctions, you have to now consider the distribution of eigenvalues and eigenfunctions. So this is a complicated form, but I don't have time to go through this. But basically, if you know already familiar with this stuff, then you can understand this. But let me quickly move to this. Move to next thing. Okay, I want to indicate in the last few minutes, I want to indicate something very important. And actually, this, as I said, that this is a very complicated calculation. It requires a lot of rigorous details. But the essence of curvature and essence of quantum matrix can be gauged can be found just by looking at this level repulsion behavior, and that is what I'm going to indicate, which is a very important physical property of accidental degeneracy, and that's what I'm now going to talk about. So I think I'm so I'm going to talk about, I think I will not talk about this Z part. So let me just confine to this part. So again, I'm taking the same Hamiltonian, the initial Hamiltonian H0 perturbed by a term H1 and H2 of strength, parameter strength X and Y. You can calculate the matrix element of the perturbation in the eigenbasis of Hamiltonian H, and it turns out to be this. You can write down the curvature of the metric of the nth eigenstate in this form, which of this form. Okay. Now, the important thing now here is you note that if you considered a 2 by 2 Hamiltonian, if suppose it was a 2 by 2 Hamiltonian, then there would have been only 2 levels. Okay. Now, 2 levels, let us look at the 2 levels. How do you write down the 2 level distance, 2 level repulsion? Okay, if you are considering a 2 by 2 level, it can be written in, let's consider the Hamiltonian is H. The energy levels can be written in this form, and where the discriminant T is this. So I am considering now a Hamiltonian 2 by 2 Hamiltonian. So that means this Hamiltonian H is 2 by 2, and I'm using now notation small h. Here. So it can be 2 by 2 Hamiltonian has only the diagonal parts and the off diagonal parts, and you know the energy level, both the energy levels can be written in this form. Now look, the energy levels, both the energy levels depend on information about H11, H22, their difference, and a third term. Forget about this one. Okay. Or keep it. Okay. So real part and imaginary part, if H is complex, or if complex Hermitian, then there will be a real off diagonal terms will also have a real part and imaginary part. So let us look at the 2 by 2 Hamiltonian. Forget about everything. The two energy levels of a 2 by 2 Hamiltonian, the energy levels are given by this. The question we are asking, this is the positive, this is positive. Now, the distance between the first level and the second level is decided by this. This term is common for both of them. For E1 also has this term, E2 also has this term. The distance is 2D between E1 and E2. That's what I have written here. But D depends on how many parameters? D depends on one parameter. This is a difference of one parameter, two parameter, and the 3 parameters. 3 parameter only if the Hamiltonian 2 by 2 Hamiltonian is complex Hermitian. This term is not there if it is a real Hamiltonian. So, or in general, if I want to say that discriminant D, which decides the distance between two energy levels, depends on n parameters, where n is 2 if the Hamiltonian is real symmetric, and n is 3 if the Hamiltonian is complex Hermitian. So that means two levels can be brought very close just by varying 2 parameters, or by varying, because D can be controlled just by varying 2 parameters or by varying 3 parameters if it is complex Hermitian. Okay, so that means, and as I said, for both curvature as well as metric trace, the level repulsion plays a very important role. Okay, so level repulsion can be controlled just by varying two parameters. If your Hamiltonian is real symmetric and complex Hermitian, then you need to vary three parameters. Okay, so that means curvature and the geometric trace can be controlled just by governing two parameters or three parameters. This is called the codimension of the level crossing. And you see, now I don't think I have time. So just by using this codimension idea, you can simplify, because you can ignore all other details of your curvature. Okay, because I keep going back, because look at here. I said that the nth order geometric trace can be written in this form. But I said this term is not going to play a very important role. This term is going to play a more important role. Most dominant term is this. So naturally, if you just want to assess the strength of G, okay, so you have to see how this is what role this plays. So therefore, and this is controlled by the codimension idea. So that's why just by using the codimension idea, the calculation of the statistics of curvature, the metric trace as well as curvature becomes very easy. Of course, I don't have time to get into all those details, so I will not get into details. But here I'll show you on the one more picture, that because as I showed you that there is the numerators of the metric trace and the is different from the curvature, while the numerator is positive always. Curvature numerator can take negative values. So naturally, even at the avoided crossings, because of the numerator, the trace can become much larger in the curvature. So that's why you see here the picture. Now I'll show you more pictures. We have done the calculation for using the detailed calculations also, and that this codimension idea actually works very well with the detailed calculations also. And now let me just show you the the numerical results. So here we have compared. So this is showing the distribution of quantum metric trace for 2 by 2 Hamiltonian, 3 by 3 Hamiltonian, 5 by 5, 10 by 10, 50 by 50. And here the red curve is the theory. And as you can see, theory agreeing very well with the numerics for small n. But as you go to the large n, the theory starts deviating. Because I did not have time to give you my theory, but theory actually was dependent on some approximations, and those approximations are not so good for when you are considering very large n. This is, of course, just the cumulative effect of the same thing, of the distributions. Okay. Now, okay, so here I showed you for the case when you were considering the real symmetric Hamiltonian's curvature, the metric trace for the real symmetric Hamiltonian. Now I'm showing the metric trace for complex Hermitian, and again the agreement is good for small n, but deviates. It is for intermediate n, but again when you go to very large n, again it starts looking better. The theory agrees well. Okay, now let me just skip this. Again, the geometric curvature, you can proceed like this, and here is the curvature distribution. Now this shows for n is equal to 2 case only, but now it is showing at different parameter values. You see, although you are changing the parameters, xy is 0, 0 to xy is 1, 0, and you go to x 10, 10, but the shape of this thing is not changing. So naturally, the behavior near the origin doesn't depend on the parameters, but that you already I have indicated, because the behavior near the origin is governed by behavior. I said it wrong, because behavior is dominated by the by the level repulsion, and that is the reason that you do not see much effect on the shape and it can be removed out. I have, okay, this is the detailed formula. I could have kept showing you the figures. Let me just see how much time do I have. Yeah, I have almost 5 minutes I have. So let me now indicate to you the last thing. Okay, as I showed you that the level avoided crossings or accidental degeneracy, there are many words used to describe how close two levels can come to each other when you are changing the system parameters. Uh, it is also called level repulsion, accidental degeneracy, or avoided crossings. So I showed you how avoided crossings plays a very important role in context of curvature, geometric curvature, in context of quantum metric trace, both important rules, not only for condensed matter physics, but also for quantum information. Okay, but now I am showing one more thing which not much talked about. But this is not my work, this is not our work, this is the work I found in literature, and there is even in quantum entanglement, if you look at mm, this Hamiltonian, which is Rabbi Hamiltonian, okay. What is this Hamiltonian atom? An atom with a single valence electron in the ground state with orbital angular momentum, L is equal to 0, in the presence of a magnetic field B in the Z direction. So this is a magnetic field and this picks up on the Z component of uh, the Sz as well as the nuclear spin, and you are considering the coupling between the nuclear spin and the spin. Okay. Now, so question is, if you consider now the entanglement between these two spin degrees of freedom, somebody studied this, and this is, I must have given some reference here. Did I give the reference here? Yeah, reference is here. This and okay, so they show the energy levels, and as you can see, the energy levels of the Barrett-Rabi Hamiltonian for hydrogen atom as function of the magnetic field. So they are plotting the energy levels variation as they are changing magnetic field, and they are also plotting the entanglement entropy of the spin degree of freedom and the nuclear degree of freedom. And you see where the avoided crossing is occurring when you are changing the system parameter, and system parameter here is the magnetic field strength. The von Neumann entropy, that means, which is also called the entanglement entropy, the entanglement of the two spin degrees of freedom becomes very large. So actually, so you see, and they have many more results like that. So you can, if you are interested, you can go watch that. So it seems avoided crossings have to play a do play a very important role in physics of these random states. Okay, so now I have come to my conclusion. So this is story so far. Distribution of both quantum metric as well as geometric curvature show same asymptotic behavior, and that can be because both asymptotic behavior can be calculated, depends on the, because as I said, asymptotic behavior means large range, large values of these of geometric curvature and quantum metric, but large values are both of them are controlled by the denominator. Denominator is the level repulsion, which is of the same order in both the cases. So naturally, it will lead to the same asymptotic behavior. Co-dimension argument applicable beyond ergodic random states. If you know GOE, good enough. Otherwise, I will use the word ergodic random states. Avoided crossings known to affect quantum entanglement too. And I have not talked about these details, but different scalings for distributions of metric for random states, depending on whether your system has time reversal symmetry or no. Knowledge of quantum metric essential for understanding many phenomena, okay. While for such, even for those cases where curvature is 0 and you cannot use curvature. So direct measurement of both the Berry curvature and quantum metric in a high finesse planar microcavity together with related anomalous Hall drift reported by these people in 2020. Okay, let me see. So topological effects are not encoded in the energy spectrum of the system, but rely on the non-trivial geometry of the eigenstates of the Hamiltonian, and therefore it is important that makes consideration of metric, which tells you about the geometry of the distance, and the quantum curvature, geometric curvature, which tells you about the geometry, important. And okay, and you can also use both of them to characterize the entanglement. For example, maximally entangled state, vanishing metric, curvature state, separable state, large metric, curvature states. Okay, thank you very much for your attention. Yeah. Hello.
Thank you, Professor Shukla, for delivering a nice lecture on this geometric curvature for random states. In particular, how a geometric phase can be used as a tool for the analysis of the quantum information. So now this talk is open for discussion.
Actually, I have a question.
Yeah.
The thing is, like you talked about this quantum energy state in quantum Hall effect. This curvature are somehow related to Landau levels. Is it not? If Landau levels can be used as a qubits or something like that, because these are discrete energy levels. Here also we got nice two-level system, but
yeah, so people have, there are people who have looked at these, I mean, they have calculated the quantum, the curvature for Landau states. And so there is a lot of work in that direction. Yes, you can do that. And regarding whether you can connect it to the entanglement, as I said that this is a work I found. And after that, there's a lot of work has been done. People, I mean, so yeah, so there is literature already. People have studied this kind. So your question is correct. You're valid. Yeah. But
okay,
look, but one thing, what we are talking about is, see, my whole, of course, because I had to talk a lot about introduction, basic things. Therefore, I could not talk about the main thing. My thing was not only talking about curvature or the metric trace for a given state. It was about the statistics, because what I was trying to motivate, because when you are dealing with the quantum, when you are dealing with the many body systems, the usual operators, the Hamiltonian is so complicated that you cannot calculate it exactly, even if there is no disorder. And that leads to, you have to consider the ensemble of Hamiltonians, and therefore you have to consider the ensemble of statistics of all the physical properties which you are interested. So therefore you cannot just talk about geometric curvature of the state. You have to talk about the statistics of curvature, because if you talk about the curvature of the single state, which Hamiltonian representation you are using, because you can't even define your Hamiltonian exactly. So it makes sense if you talk about the statistics of the curvature. So when you talk about the curvature of the Landau level, okay, so if you can define the state exactly, can calculate, of course, go ahead and calculate, but it is not, because always there will be a disorder. The real systems will always have a disorder. And usually when you solve the Landau level, you do a lot of approximations. You neglect the interactions between Landau levels. You neglect the interactions with various other things. Ultimately, actually, it is not so simple. So you have to consider the statistics of curvature, not single. That's it. That was the main idea.